Well, I think I'm audible now. So, quick second stream to follow up with the entities. We just got a separated entity struct and a entity manager that takes care of the creation as well as, let's say, iterating through every entity available. We've separated out entities from everything else. I'm just going to quickly generate this particular part. I need to make the constructors or move constructors in the others. Interesting. Doesn't seem to allow me. Convey definitions. For what? Extension, edit, delete code. Anyway, I can do that later. So the goal of this particular part of the stream is to set up bindless textures. So bindless rendering is a way to avoid using all that descriptor set, the kind of mess we saw at the end of previous stream. So since we don't want to pass around the descriptor layout and to create individual descriptor sets per material, we will just create one descriptor set that contains the data, well, not all the data, but the textures that we will use through the entire program, right? A single descriptor set that has everything. This is not something that Vulkan supported during Vulkan 1.0, by default at least, but now we have this kind of a feature, so we can use it. So you see, I want to remove the descriptor pool dependency, and that is something we can look at now. So first thing to do is to create a new class, because this one will be fresh. It won't be a refactor. I mean, there'll be parts that will be refactored, but most of it will be fresh. So texture manager, edge file, the what? Interesting. I don't see why it's saying that, but let's do this. Hopefully that would be enough for it to know where to put the file. If it doesn't work, we can always figure it out later, right? All right. So now include apt state. Does that work? That works. So it's in the right folder. It's exactly where I want it to be. Now, texture manager. One thing for consistency is that everything is defined as a struct for now, and later on I'll make everything a class. It doesn't make a difference. In C++, there is no difference between struct and class, other than the fact that a class is private by default and a struct is public by default. They could have just had one single type, but they have two, simply because C++ wanted classes, because it's C with classes, right? While to keep C compatibility, they had to still support struct. Anyway, so that's texture manager H and texture manager C, CPP. That is all fine. Now we need to create textures. So how do we create textures? We just say another struct. As you can see, I'm making an inner struct. The idea is I wouldn't use this from the outside. This takes a VK texture, so VK image. And I'll include a Volk here. So include Volk. So that's VK image. VK VMA allocation. So that's right there. Save and some allocation. VK view, image view. So just gonna find a view. And sampler, as you might have seen, has no dependencies on the texture. So I'm not actually adding it inside my texture here. What I will add, however, is the extent of this texture. That can come in rather handy. Okay. And it's an extent 3D because images can use 3D textures. Another thing that I can track is the format. And since I can track it, I should track it. So format Also because extend 3D is 3 floating points. Adding this makes it 4 even number. This is 8 bytes. So this being 12 bytes means I'll be wasting 4 bytes anyway. Add a format which completes those 4 bytes, let's say. Okay, so that's a texture. We don't do anything with respect to texture to say we create a texture or something right now. What we instead do is texture manager will take a render device forward declaration as a pointer. So P render device. And it will use this render device to create all the textures it needs to. Okay. So based on this, you can now just allocate and create textures. At the same time, instead of providing you with a texture or a pointer to a texture, we will provide a texture ID. Now, this can be done in 2 ways. One is to, I'm going to move it outside actually. One is to just call it texture ID. The other one is to create a class called ID or struct called ID, make it templated, template type mail T, and then say ID of T, right? So this doesn't matter, but here we'll have a texture ID. So using texture ID equals ID of texture. What that allows us to do is just use the same ID everywhere, and it should be able to, manage it through type safety, like with type safety, sorry. So I'll use this. So we have type safe texture IDs, right? They're aliased, but that's fine. I'm going to call it RIDs because Godot calls it RIDs, and RIDs sound just fine for me. Inconsistent naming, add it to an abbreviation list. There we go. Okay. So what does an RID consist of? Consists of a UN32T, which is the index. And that's all it has. In a class, right? Which contains an index. We'll keep it a struct, private index. So this cannot be modified by anybody outside of whoever has access to the index here. And I'll give you a small secret. Nobody has access to this index here. Okay. So effectively, this will be a black box, the size of an index. We could use enum class. That's also another alternative available to us. And this index needs to have an invalid value, right? Because RIDs can be invalid. So now there are 2 choices. One is the uint max value, which is 0xFFFFFFF hexadecimal. So every bit is set to 1. So it's the max possible value of this thing. That can be one sentinel value that we use as invalid RID. The other option is to use 0 as an invalid RID. And 0 being a default index for anything. Sorry, 0 clearing being a default thing makes it quite much easier for us to use the invalid index, right? Because by default, it is invalid. Also, what we can do is instead of having an invalid state, we let the invalid index point to an actual texture, because pointing to an invalid texture can cause the GPU to hang up. So instead, we manually make the invalid index have a specific texture. And in that case, having FF, like the max value, is not good because we won't have 2 billion slots. So what I'm going to consider is the default value is 0, right? So index is 0. Of course, it's private, so it's called mindex. And RID should be able to initialize itself automatically. Another thing I can say is public. So now we'll create a thing called null ID. RID null return something with dot m. I don't think you can do dot n next. Make a private constructor for this because we have to. Oh yeah, static. Forgot about that. So our ID takes a urint 32t const index sets m index to index and nothing else, right? Explicit. Another one where it takes nothing, default constructor, which we can just say is default. But also you can just say this. So both are equivalent. And remove that. That works out. It's cleaner to use default. So default it is. All right. So that's the default constructor. This does nothing but return a default value. So null will be automatically default. And by doing this, there's no way you can actually create an RID, right? These are private. So nobody actually can call the default constructor either, except RID itself. And I'll show you how or why and what kind of a weird thing do we do to get RIDs to have a value. But we'll come to that later. First, we take a render device here. Second, we get textures. So that's textures. Should I have a prefix for arrays like k textures? I think so. It makes sense to me. So I'll make sure I add that to everything. But for now, this is fine. Count UN32T because I don't think I will have that many anyway. Similarly, UN32T for capacity. Because again, I don't think we'll be adding that many. All right, so this is texture count and capacity. Textures will be allocated and deallocated on the fly, more or less. Let's say we will allocate, deallocate textures as required. What we do need to look at is how we get things out of texture, let's say. So what I mean by that is how do we create it, how do we use it, and how do we delete it? First of all, between creation of a texture and using the texture, we shouldn't need to do anything. RID should be enough. The same RID that we use on the CPU should be a valid RID on the GPU. So that is exactly what we'll do. Secondly, textures that are created here need to be freed at some point, and that will create holes. There are two options with holes. One is to create a sparse set, which is what I will do for entities, where having an index 1 and an index 3 does not mean that they have a gap of an index 2 between them. Because in a sparse set, what happens is index 1 will point to something. So let's say, for example, index 1 points to 1. I can show it on the screen here. So 1 points to 1, 2 points to 2, 3 points to 3, and so on, right? Then we come in and we say we don't want this anymore. So we delete element 2. So normally index 2 should go away, right? This is normal indexing in an array. But in a sparse set, what we do is we say 1 points to 1, which points to 1, 2 points to 2, which points to 2. So this is external index. This is internal index, inner index, whatever you might want to call it. And this is the data. So maybe for data, I'll call them K1, K2, and K3, right? If I delete 2, right? If I ask to delete 2, that means this has to be deleted, but that doesn't mean this gap needs to exist. What will happen instead is this 3 will point here, which points now to 2, and A3 will go there, right? And this 2 will become, like, it points nowhere, right? So what happens is you keep the data still contiguous. So in entities, for example, we are iterating through all entities and there will be empty entities in the middle. It is currently invalid. It has a bug that is known to us. And once we do this, sparse entity sets, that will be fine. But for textures, because we're communicating between GPU and CPU, this will be an additional level of indirection on the GPU. We don't want that because GPU is not as good as CPU at indirection and it is doing a lot more at a time. So what we want to do is for GPU to directly be able to access things. So it will be a direct indexing system, which means there will be empty spots in the middle. So these empty spots have to be handled. And in order to do that, we'll create what is known as a free list. So what's a free list? A free list is nothing but a linked list. And it, keeps free elements in the middle. So let's create that. And yes, I am manually creating my own linked list here because the built-in linked list assumes that the linked list contains valid data. But in case of our textures, when we have a deleted texture, all of this data is irrelevant to us. So all we care is if the data, like if there is a free list or not. So we create a free list node. So either it will be a texture or it will be a free list node. Okay. Which points to a free list node in the forward. So P next. And it will point to one in the back. So P prev. That's a free list node. That's how it is. And in simple form, each free list, so free list will contain a free list node. It should contain, yes, a free list node P next or P front. Actually, the best way to do this is to have the free list handle it using a free list node itself. So a free list node head, a free list node tail. And as you can see, these are not pointers. These are actual allocations on the stack for the free list. So an empty free list is the one where the next of the head is the tail and the prev of the tail is the head. So the default free list is a pane. This will be private. This will be public. So M head again, M tail here. So M head, where the P next will be M tail's address and null pointer on the P pref. I will write this manually because it's much clearer than just having it automatically figuring it. Even if ReSharper or Visual Studio is adding nice data for me. So null pointer and P pref equals M head. So by the time constructor is called, all of this memory is second, right? So these pointers are 5. But this set of pointers means that free list cannot be moved. So free list constructor with another free list. So other should be deleted. So move constructor is deleted. Copy constructor should be deleted. Because these don't actually own the memory. So this is nothing you can really copy. So operator equals, that's an assignment. And similar, this has to be ampersand. So operator equal. This one is a move constructor or move assignment, and that's also deleted, right? To delete all of them. We don't need to do anything in the destructor either. So this we can just say is default and it should handle itself. All right. So this is the base free list. What we also need to do for a free list is to take and give. We don't care. We don't need to call it anything else. So we just have to call it take and give. So, or, alloc and dealloc or something like this. What I will call it is just pop and push, I think. Keep it with a list or a stack. It's more of a stack. Okay, anyway, so push gives you a void, takes in takes in a free list node pointer. As you can see, it's a pointer, like it only takes a pointer. And let's make it push back. So we'll push back into it and we make static. Not really. So M tail, so that's the last, dot pprev equals pnode now. Should be. But first tail dot pprev dot pnext is equal to pnode. So what I'm saying now is the one before the tail. So if you take it like this, some x points to tail. So what I'm trying to say is go from tail to x, which is pprev. So this is the given prev, right? And for it, say that the next, so prev next is pnode, and say that the tail prev is pnode. And then we can also set the tail and this thing. Okay. So once this is done, pnode, actually we can take this. You can say that as prev. So free list node pointer, or what I will do is I will do a using. So using node equals free list node. So this becomes node pointer, which is easier for us to write. Node pointer. So node pointer prev equals tail dot pprev. This might as well be head, we don't care. Prev dot pnext is pnode. Pnode dot pprev is prev. So we have first, I'm going to remove that, but we have first created set prev as previous of pnode, and then set tail as next of pnode. Tail next, this should be pnode. Should be m tail ampersand, of course. Okay, next, bool empty. So this will check if it's empty or not. We do that by simply checking if p head, okay, this will be const. We do that by saying p, so m head dot p next is equal to and of m tail. Return. So if the next of the head is the tail, then we've finished it. No discount. Cool. Let's push back. We'll add pop back. So pop back. This will guaranteedly assert. So we could do two things. We can do an assert or we can do an optional. I think I will lean towards optional. So optional node pointer. Or just node pointer, right? We'll do optional as a try pop back if required. So anyway, pop back, what it will do is it'll try to pop the end. First thing it will do is assert. It means to assert that this is not empty. Okay. If it's not empty, Then we have something that is available in the back. So we'll take campaign.pprev, okay, and we'll use it. So again, there are options. We can pop from the front, make it a queue, pop from the back to make it a stack. I don't particularly have any. I think it'd be better to pop from the front to implement the queue first. So, because reallocating the same thing, somebody might not have cleared their IDs. They might still be holding on to the old ID. It'll be easier for having pop front because, it will handle that. Anyway, so what we'll do is mhead.pnext. So this is the element we want. So node pointer element equals pnext. Okay. Now, since that is popped out, we will say element pprev pnext equals element pnext. It's one of my favorite things to do. And element pnext pprev equals element pprev. So for the next, the previous should be my previous, and for the previous, my next should be its next. And effectively, you removed yourself out of the equation, right? And then return element. That is done. This is const. This makes no sense to me. It shouldn't be const. It's just because it's not aware of the idea that this is modifying things inside pop front. Okay, and that's all. That's all we need from the free list. So then we'll make a free list here, which says free list, right? Nothing else. Cool. So far, we're doing fine. Now, this texture manager, once it's allocated, will do a few things. So we can say texture manager constructor, which will take render device pointer p-render device. It will take texture pointer a textures. It will take the count. So ul32t count. The count will be 0. It will take capacity. And the free list will be default initialized as well. Again, so now we can start it. First things, p-render device is p-render device. Next, a textures is a textures. Next, capacity is capacity. And the others are default initialized, so we don't have to bother with it. Initialize member count. Of course, it was count. Count 0. Const. All right. So that creates texture manager. The destructor of texture manager will just say assert lot is init a textures really. So yeah, that works for us. Destroy. So void destroy, which will actually do the destruction. Destroy will be, so textures will be just winked out. What we want to do is we want to actually destroy each texture that is still in use. So how can we go about doing that? So free list holds a list of textures that are not in use. So each of these textures will have some information. So all of this texture will have some information in it. There's no way I can delete all the other textures without, having that particular thing in there. So what I will do in destroy is first I'll assert, okay, not assert really, but if, this should be debugged. So hashtag if define debug and if, so this is only if it's debug. So if it is debug, then I want to check if A textures, count is greater than 0, SDL log error, category SDL log category error, and the error says percent %d textures still, this should be percent here, textures still allocated, and percent %d will be count. Okay, so we say that many are still allocated. We need to manage that at some point. That is only if it's debug. If it's running, then we don't particularly care. In here, all we have to do now is to take, pop each node from the free list. To do for each, I guess we need begin and end in free list. So, and it needs to give an iterator. It can't handle just, free list nodes. So it has to have an iterator. So struct iterator, and this one will contain a free list node internally. The iter and operator plus plus. Okay, must have a return type, void. I don't think void works, does it? Yeah, it should return an iterator. This is a prefix operator plus plus. I need to check how to do prefix operators. Prefix plus plus C plus plus. Recommend. So yeah, prefix operator just takes the operator plus plus and doesn't take anything on the outside. In parameters only used to do a dummy. So this is fine. It will return the next. Construct one using that. Right? So just keep doing next. Const. Says ampersand, but makes sense. So this won't be const. It does an ampersand. It should actually just increment its own p-iter. So p-iter equals p-iter to next and return this, star this. Okay, that's it. So it should handle iteration. So we need to return a begin and end. So we do a begin. So iterator begin, which returns an iterator that is created from our pop front of m head p next, because we don't want to iterate on head, right? Head is a dummy value. And iterator end, which is nothing but m tail ampersand. This is one past the last one. Okay, so now based on that iterator that we have a begin and end. So we can do a for each. So for, and inside this for each, we can say the value of this iterator is free list node. So free list node takes a free list. This will probably not work because this doesn't have a dereference operator. I think it means the dereference. You can check. Build solution. It's a header file. It's not even compiling. Texture manager. Build again. Now it failed, right? Because not equal to is not defined. So we will not equal to in iterator. The operator equal to other iterator. Return other. So it's this ether equal to other ether. And if equal to is created, not equal to is automatically created. You cannot dereference, so we need to do that too. So free list node ampersand operator star return reiter star that returns in a free list node. And we made const. No, it cannot. So here, now we get the node, which is a free list node. And for each free list node, what we can do is we can cast this. So because we know it's a free list node to a texture. So texture pointer x equals and the node dot reinterpret cast texture pointer, then mem set 0. So it's a text 0 size of star text. Okay, so that zeroes out each texture that doesn't exist. And then we can go through every single texture. So for texture and text in iter, so we call it our own iter. We don't have an iter here, so student span. I don't want to make an iter here either. So I'll take textures and count to create one. Span. Right. And for each texture, then I can do destroy. So destroy texture text. Okay. Create member function, destroy texture. Does a void takes a texture reference, not const, and text. We can move destroy out of class scope. Done. We can generate a definition for destroy texture on the other side. What will this do? It takes a text. And for the given text, so if text dot image, so if not text dot image, return, because this is not a valid value, right? Otherwise, if there is a text dot image, we need to do deallocation. So again, assert p render device just to make sure it's there. Then if p render device exists, take render device and render device equals star p render device. Then text dot vk destroy image VMA destroy image, because we will have used in VMA. Render device dot GPU allocator. Image is text dot image. Allocation is text dot allocation. That's it. Both of these will be take. So text dot image. Take text dot allocation. Okay. That's VMA destroy image. And the next thing we want is to VMA destroy, or VMA, VK destroy image view. So we want to destroy this because, we created it and it's created from the image. So it has to be destroyed before the image. No allocation callbacks. Thank you. So image view has been destroyed. What else exists within text? So text had three things: image, allocation, view. Extent and format are pure data. It doesn't matter if they are left, but to be clear, extent equals 0, default initialization. Text dot format equals vk format undefined. So I just ensure that it is done. take a constant reference, that's fine. Okay, so this is okay. Destroy texture is here, can be made constant, but textures are within its own bounds, so it doesn't make sense to do this. This is an internal function. So on the other side, inside the texture manager, destroy texture will actually be private. All of these will also actually be private. So public and destroy texture gets moved at the left. Or enter. Is that will automatically do it for me? Thank you. And count and capacity and free list. Okay, what's your problem? Private field M count is not used, private field M capacity is not used. That is fine. We haven't yet written the parts that actually allocate this. Okay, what next? So texture manager needs the other useless constructors. Edit, generate code, copy and loop constructors. Both are delete. So that's it. Nothing else. Texture, those are the class scope. That's it. So that's all we need from there. Next comes the important, let's say important runnings. So allocate texture. This will return an RID of texture. That's texture ID, which is allocate or create texture. Okay. I'm not putting anything inside this. We'll write the definition here first, and then we will put things as we need. So we currently moved into entity creation during the material part. So here, all of this, right? We can copy and we can move it to create action. Okay. And we'll do a few more things. So first, even though we create a texture, we will not upload to it in the same run. So this whole thing with std image upload is gone, right? Second, width levels, they're taken from width and height. So these are valid values. These are valid values. This will actually be an input, the extent. So we say extent, and instead of taking 2D, I'll take a 3D extent. Extent 3D, extent. Okay. So this comes from extent.width, extent.height, and I need another std max with extent. Actually, on the other side is better. So extent.depth, right? And finally, I think I need to add another bracket. So that should handle itself. This can be another utility private function. So static calculate width levels with required width levels. It returns a uint32t. Oh, is that? It seems like a valid way of defining static, eh? So, yeah, uint32t width, uint32t height, uint32t depth, and it does this math. Return, and that whole thing becomes width, that whole thing becomes height, that whole thing becomes depth, and this entire thing here will just be called 32t max dim, and that should handle itself, right? Const. This is const. Okay. So that creates that gets us the appropriate number of myth levels. This whole thing gets replaced by calculate required myth levels, extent.width, extent.height, extent.depth, right? Okay. Again, this whole thing is even simpler because here we just give it the extent we got. Okay, what else do we need? So currently we will only support 2D images and we'll keep it to our R8G8B8 sRGB. Okay, but I will make this an explicit format and I'll move this as a VK format equals this. So we can move it in later. Render device becomes MP render device GUI allocator. There, render device is incomplete. So we leave it that way. So we'll then move definition out of class code. So life is easier if we do this. We will actually take the render device out. So assert the render device, then render device ampersand render device equals star and PM device, right? Cool. What else is left? So size was a size construction. We don't have texture data. So we don't actually know the staging buffer size. But this whole thing about staging buffer, we don't need it right now. Staging to transfer, again, another thing we do not need right now. None of this is automatic, so all of this can be removed. Submit everything goes away. Similarly, descriptor set, we don't need it. So goodbye. Material is replaced with texture, right? Texture. Which takes an image, so texture. Allocation is fine. It has nothing on it, so I will take that apart. Dot disintermissionalization. So that's texture. Allocation is texture allocation. View is texture view. Extend is extend. And format is format. This is not Rust, so it doesn't automatically do all of that for us. Okay. Anyway, so this is the base create texture function, right? Post, why not? We do post. Okay, post on view as well. So this actually does not return the correct values. Okay. So all of this is happening. We get here something else, so that goes away. Okay, so texture has been created, but we don't know where to allocate this texture, right? We don't have a location to allocate the texture. So first thing we'll do up here is we'll check if there is a free texture available. So free list free list dot empty, and we'll assert it that is not empty. We can do something like, okay, we cannot allocate, so we'll give you a null reference sort of thing, or we can assert. That is a good question there. So this, again, the API can change. So I will change it. STD optional. So it may return a texture ID, but you can't guarantee it returning a texture ID. Okay. So if it is empty, then we return std null. What's your problem? Okay. Problem is that we don't have optional on this side, so std optional null. That should be fine now. Here. So if it's empty, then return unlocked. Otherwise, it's not empty, which means I should be able to get a node. So free list node, uh, node equals and free list dot clock front. Okay, so we got a node. We can allocate on this node. And when we do the texture, so instead of taking the node directly, we can keep it as a texture pointer. Texture location, call it a slot, texture slot. And this can, what's the problem with your previous node? So this can be reinterpret cast into the right type. Texture slot has been constructed there. So texture here can do a new. This is a placement initialization. Texture slot. And this will just work. Okay, so that has allocated the texture and on texture slot. What we don't have is the index of the texture slot. So for this, we'll do a thing which is texture slot minus MA textures. So this gives us the exact location of the texture. So this will always be positive. We know this. So it's UPTR diff. PTR diff T. Okay, yeah, it's PTR diff T, but it's UPTR diff T. So it doesn't exist. Anyway, this is the index, right? What I want to do is I want to static cast it down to UN32T. Okay, it's a reducing cast. And that gives us a UN32 index. Okay, this is fine. I will also do a little bit of more funny stuff, let's say. This funny stuff comes from the main device here itself. So const expression static. So this is permanently constant. UN32T. Okay. Generation mask equals 0x FF F0. 1 2 1 2, right? So I effectively take, this is what? 4, 8, 12. And the remaining of this, which is index mask is 0x 000 FF. So this is 1 million. So what I'm saying is we cannot have more than 1 million textures at any point of time. I think that is a more than sufficiently high number. We will have 4096 generations. In fact, I'm fairly certain we can go lower. So this should be fine, which is 65,000 values. Or we can do, 7 there. So that's 500,000, which is a big enough number. And generation mask can be lot of index mask. So we don't have to look at actually managing it. All right. Okay. So what's the next step in this process? Oh, just give me 1 second, please. Okay. So what is the next step in this process? We have the index and the generation mask. We will take texture slots here. So this is guaranteed. This difference is between textures. So this will give us the index. This index is guaranteed to be less than, the required value. But what I will do is I will assert it. So during debug, we can test this invariant. The index is less than index mask, right? So index mask will tell us less than equal to. So this tells us what the index is exactly. And we need generation. That's one thing. We don't have a generation storage here. Right. Like we have nothing here that actually puts the generation in here. Hmm. So we have to figure where to put the generation. To be fair, generation can be a part of texture itself, right? This is not something that is part of a public API. This, in fact, will always stay inside I mean, I've put it outside here, but it will eventually just go inside the uh, texture manager. So, what are we trying to do? Capacity, we don't use it. That's interesting, but okay. So we need a generations, can prevent that texture itself. How many generations do we have? So yeah, and this is, I mean, it shows us a big number, but it's really just FF 7 0x 8x equals, so 32,000 generations, which is half a short, right? It's a half of 16-bit. Do we have anything here in texture that can deal with having less data? Not really. But what we can do is we can store the entire index into this. Okay. So we can store a UN32T index. And this allows us to easily fetch this index data. It does move in here inside the texture manager. We have to do a for each. So for each texture and text in std span of a textures, so m a textures and m count, the m capacity. So for each in this, U832T I equals 0. And for each texture, the text dot index equals I plus plus. Okay, so the I keeps increasing and it will keep indexing each of these automatically. One thing we also need to check, and this is some sort of funny stuff that ends up happening, is static assert. Okay, we statically assert that size of texture is less than size of, sorry, is more than size of free list mode. Of course, this texture can be, so this both RID and texture can both be moved below free list. Okay. Yeah, so static assert size of texture is greater than size of free list node. We can also put, I think, and layers and texture is used inclusively by free list. Okay. And another one, which is offset of texture index is greater than free list node, size of free list node. So index should not be overwritten even in invalid state. Right? So these two static asserts, we can move it inside texture itself. We can't. So we're gonna keep it right there, but we're gonna make sure that we guarantee these so that we don't end up with corruption, let's say. Okay. So this index is still a part of this, but not overwritten by fairness node. So the index keeps alive between users. Okay. And whenever we get this texture, we also take M free list and we push back the node. Okay, there's a small issue with this. And the issue is also quite, it's not difficult to understand. The issue is we will end up using the last index first because we're pushing back. Okay. And we're popping front. So what I'm going to do is I'm going to add pop back up. So you're pushing back. I want to add push front. It's not that difficult. So push front. So prev, instead of prev, we use next equals the next of the head. Then next. So the prev of p prev of next is p node. And the p next of this thing is next. So set next as the next of p node. And set head as the prev of p node. P node, p prev equals m head, and m head p next equals p node, right? So this is push front. And by pushing front, we will ensure that we pop from the right location at the start. Okay. And it takes and text. We'll do a reinterpret cast on it, on and text to the free list node, right? Free list node pointer. Okay. So that will handle itself. We do a push front, all is good. We'll say it's a free list node. So that should figure itself out, I believe. So generation here is by default 0. So default generation is 0. And we don't do typed, like we don't have type tags there because there's nothing except textures that will actually be RID'd. Buffers use something completely different. So there's no way we're going to have clashes, let's say. Okay, moving on. This is the texture index. All good here. Build solution. Let's see what's happening. Create texture, normal control paths, return a value. Entirely understandable. So texture creation. Explore. Say so. Never mind. Leave it as it is. Host. Okay. Where are we? Normal control paths, return a value. Because we were here, we asserted the index mask is less than this. And we don't even need this anymore. So what we can do is we can take the texture slot directly. Dot index. Right? And here, during this allocation, dot index equals, so you enter DUT const index equals texture slot index. So this is important. Note texture slot reserves index between uses, right? We do mem set it to 0 after the end somewhere, but that can be handled separately. But okay, so index equals index. So that just ensures the constructor doesn't mess us up. It will add the right index back. And we can ensure that index and index mask is less than or equal to index mask, which is a guarantee. So that's pointless, right? So this is pointless now because index is preserved from here. So we just return index. Now there's a thing, index is uint32. So how do we get texture ID out of it? So texture ID, reinterpret, cast, texture ID from index. So what we are trying to say here is custom const or other qualifiers. There's a const somewhere. Oh, that makes sense. So effectively what we did was we took the index, we cast it as an RID, and we passed it on, right? So this texture RID is never constructed. It's not real. Nobody can construct it, including us. But we just internally, you know, do some no byte memory hackery to create texture ID. Of course, there's the alternative of making it a friend, right? Make texture ID a friend of this class. There's no real problem with it, but I don't particularly care. Okay, so that creates the texture ID. Return us a texture. How do we free it? This is destroy texture here. What does destroy texture do? It does those. As you can see, it takes everything except, so note, do not edit index. And we can guarantee this by taking the index here. So auto uint32t const index equals 0. There's going to be a little bit of a interesting thing here. So you'll see x.index. Okay. So index is assigned. We will split it. So uint32t const generation equals index and the generation mask. Generation offset. And I need to create that. So generation mask, copy paste to there, offset. What is generation offset? So it is how many bits is this shifted to the right? So that's 4, 8, that is 16, and 3 more bits, then 16, right? So that's 19 bits. So if I shift 19 bits to the right, I will get the generation in the right location. Or so I think. This has to be verified. How do we verify it? We shift things 19 bit to the left. So do a static assert. Generation mask reduced by generation offset is exactly equal to, and it should be equal to FFF and 16 minus 7 is 9. 9 is represented as 9 itself. It's not correct. Why? To the animates to false. Okay. Okay. False. Is it less than? It is in fact less than. Well, this checks out. This checks out. It is okay. 7, 6, 5, 4, 3, 0. This generation offset a bit too high then. So that doesn't work. Okay, what I can actually do is I can say generation mask with generation offset and 0x1 is equal to 0x1. So I want to save the lowest bit as set, right? The value is to false. So lowest bit is not set. Not set, not set, and it's set. Not set, and it's set. Okay, so I had it correct. I think. Yeah. So 19 shifts bring it to the exact location it needs to be. Alright. What next then? So this evaluation tool, this is fine. And we need to also ensure this is the first one. So and that. So with this, sorry, sharpening. So that's fine now. Yeah, identical operands, of course. Generation offset minus one. Minus one. And this should not be. So that checks if it's exactly in the boundary or not. Okay. So that is fine. Okay. That is fine. Moving back to destroy texture. So we get the generation. We get the UA3050 cost number index equals index and index mask, right? So it gets the index, it gets the generation. We move down here. Now we assert that inner index is equal to text dot index and index mask, right? So we guarantee this promise. Index not by fault. Index should not be modified. Okay. At the same time, the generation should be increased. So what ends up happening is text dot index is equal to text dot, so it's actually equal to inner index or generation plus one shifted by generation offset. Right? So now what's happening is the generation keeps increasing. So after we assert that, we also assert that text dot index is strictly greater than the original index that we had pulled out. Should increase generation should increase, right? We're not just testing generation because you already know index is the same. Cool. With this, the texture has been destroyed or freed, more like. We also need to add this texture into the free list. So free list dot push back text. Okay. So cannot convert texture pointer to free list node pointer. That we can do using reinterpret cast. And that's it. Okay. Now, what else do we need? So this has been done. All of it is done. Destroy is done. So texture is managed now. It can create a texture, and that's all it can do right now. Okay, let's look at the interface again. Calculate requirement levels. Definition has to be moved out of the class. Paused, paused, and final paused. Okay, that is okay. Just move it out of it. Let's go name class. This destroy and this destroy are different, so okay. So we have a create texture, we need a free texture. So void free texture. You can see I've deliberately named it differently. Texture ID, and it takes a texture ID for text, right? So generate definition. So it frees a texture. How does it free it? So first it checks if it's a valid texture ID. So how do you check a texture ID is valid? Well, first to do assert, not assert, but if return, okay, if float is valid ID X ID, okay, call it text ID, applying name refactoring, this is fine. Create a member function called is valid ID, takes the texture ID, not ID. This is fine. And we generate a definition, okay? The way to use this definition is first you get, so you have to first convert it to uint32t, index equals star, uint redcast, uint32t pointer of VRID. Okay. Valid ID. Yeah. Next, from index, we get the index mask. So uint32t inner index equals this. Generation equals generation index generation mask. And reduced by generation offset. So once we have inner index and generation, first we check if inner index is less than equal to capacity. So if inner index, actually we don't even need if, we can directly start returning. So return inner index is less than equal to capacity. And because we can have holes in there, the count isn't actually going to be very useful with respect to telling us if a particular location is free or not. And to be very honest, we don't actually need the count and capacity anymore, right? We have the count to do a bit of bookkeeping, but we don't actually use it. So inner index is less than capacity, something we test for bounce checking. Inner index is positive, so it doesn't matter, it will always be positive. Generation is greater than, no, generation is exactly equal to the generation inside that texture location. So if, okay, fine, this is different. If inner index is greater than capacity, return false, right? Then if it is less than capacity, then we can actually use the inner index to index the textures. So MUA textures inner index dot index, that gives us the index. Okay. And you just have to return if this index is exactly equal to the other index, right? We don't even need the generation. because every time we free, we increase the generation counter, which means if it has been freed, then this has automatically, figured itself out. Let's say is valid ID, is valid ID is to be const, and that's done, right? Next, free texture, discard. In fact, the one that really needs no discard is this one, because otherwise the texture ID is neat. So free texture. So if not valid ID, we just return because there's nothing to be done with it. Otherwise, if it is a valid ID, then we free this texture. So what we will actually do is we'll take a reference to text ID. Free texture will take a reference to text ID because this will internally modify it to null, right? Sort of const. Okay. Take a value. It's fine. Take a value. Okay. Anyway. What are we doing? Freeing the texture. How are we freeing the texture? So first, we check if it's a valid ID. It is a valid ID. Next, we need to get that texture. So for that, we will actually add a little helper function again, which will be internal to us. So texture and fetch texture. Okay. And the first texture actually takes a texture ID to give us a texture. So texture pointer really, because this RID must be vetted. So texture takes this thing and it only takes an index. So event WT, right? It will always give you a reference. This needs to be externally validated. And what we can do is we can actually add an internal type called valid ID that we can use for this stuff. Okay. So anyway, fetch texture, generate the definition. Fetch texture is internal. It has to be validated before we do anything with it. So valid ID. We don't actually need it if it's a event 32 that's already been separated out. This should be texture ID. So texture ID. And what this will do is it will split this texture and then check it out. So again, static, no, where is it? We do it often enough that I think we should remove this. So texture name is fine, text ID is valid here. So this reinterpret cast happens so often that this whole thing can be converted to an external function. And yeah, so I'm basically doing plumbing work at this point. If you want to tune out, you can. Struct index U32, U32T generation, U32T index. All right. This might not be the best, but it's fine for now. So fetch texture index is actually constructible from texture ID. Never mind. We don't want this. Don't use it that often anyway. So what we do use, in fact, is fetch texture here. This valid ID is done. So fetch texture should be valid. So okay. What is this doing? What are you making? It's a renderer in Vulkan. I'm doing a specific part, which is a texture manager, so that we can add bindless rendering. Okay. What what is this going to do? So first it will fetch the index. So that is valid. So right here. So it will take this exact thing. Okay, it is found in the index. Now from the inner index, actually I'll rename this later. From this inner index, we'll return star of a, I'll just put a textures in inner index, and that will be a fetch texture. So this is it. Fetch texture unchecked. Fetch texture unchecked. Okay. So create is done, but I want to use free texture, yeah. So texture, does it matter? Texture equals fetch texture unchecked, text ID. So that gives us the texture. And now we can free it by doing a destroy texture on the texture first and following it up. I think, wait, destroy texture itself is going to free it, so we don't have to bother with that. So that is freed. Destroy texture. Yeah, it has to free list. Hmm. Okay. Anyway, so this effectively is all we need from here. Texture is created, it is freed. That's a fair enough API. First. Okay, that's a fair enough API. The texture is going to be allocated on this easily. Now, nothing from the outside can actually write to these textures. That is understandable right now, but we need a way to actually write to them. So, void upload texture, and we'll take a texture ID. So, texture, you will leave it alone. So we can do that later actually. So right now we can actually just say we can image fetch image deprecate later, make a macro for deprecate later. So just that define deprecate July 2025, let's say. Okay. So macro utils deprecate July 2025. And duplicate July 2025. Became a fetch image. So that should be fine. This gives us an image for a given texture ID. So that did itself. And different texture, red. So fetch image takes a red, and it will do the fetch texture unchecked, sort of, but it will also return optional VK image. Okay. So we return optional, it will first assert a valid. So if not is valid ID, red, return has to be well up. That's it. And otherwise return fetch texture unchecked red dot image. And we can move this out of the definition, out of the class zone. So now we can let it post. Okay, let's fetch image. So what's happening now is we can just get the image out of this thing and use it outside as we need it. For image, we can do one for image view. So image view to generate the definition, and it's going to be the exact same definition as image. So fetch texture object dot view, right? And we can also do an unchecked version of these. So, but it's fine for now. These are not going to stay much long. They're not going to stay for very long, so it's fine to have to give out just the optionals. Okay, what else do I need to do? So with this complete, I do actually write a create function for this. So texture manager pointer, texture manager create. The create will take global memory, mem, yeah, whatever the texture is. So that's a render device pointer, render device, and capacity. So ULT or DUT max count. And here we just need to render the definition. So first things first, based on the max count, we need to get allocation for the texture. Texture pointer allocation equals textures. So it's called textures, I think. Textures equals mem allocate. So what's the size? It's max count multiplied by size of texture. And the whole thing has an align of texture. So that gives us textures because this needs to be reinterpreted. Okay, that gives us textures. Render device we already have. We just need an allocation. So std byte pointer allocation equals mem allocate size of texture manager. Align of texture manager. So that's the allocation we need. So new allocation, texture manager, render device, a textures, this textures, and max count. Then we return that. And that's simple, right? Nothing we have to really bother with. Things we have to check is if textures, if not textures, return null pointer. If not allocation, return null pointer. Okay, so with this, texture manager should be created. I'll just move this out the bottom, and there is a solution nodes. Okay, that's fine for now. App state. So now the app state needs a texture manager as well. State, entity manager, texture, actually we did before, texture manager. We don't particularly care because we use forward declaration for everything. There you go. Texture manager. And since we have done that, it should ask for it here. So texture manager power to texture manager, which means in the definition again, we need a texture manager pointer. Texture manager. Yes. Okay. That's fine. Texture manager. Okay. And we need to create the texture manager. So here we take entity, here we take texture manager. So texture manager pointer, texture manager equals texture manager create. Texture manager included. Create. Takes a global memory. Render device. Max count. Let's say 10,000, right? If not texture manager, then SDL log error. Texture manager. Fail to init. Render device. Destroy. Destroy window. Return null pointer. And here we just have to add the texture manager to the string. Okay. And with that, similarly, we need to destroy the texture manager here as well. With that, we should be able to move on. And the reference solid parameter. Hey, build. Succeeded. This is fine. If we run it, it will run. Question is inside entity manager, how do we get the texture manager? So we need the texture manager to, so we need the entity manager to have a texture manager if you want to do this. I think the better way to go would be for render device to handle texture manager, because at the end of the day, textures are a part of the rendering system itself. So that was a bit premature, let's say. Should have done this instead. So at the end here, texture manager, at derivative, you want to do instead is struct texture manager. Let it be a forward declaration. Semicolon. So that's done. Here, we'll need a texture manager, pointer texture manager. Okay, that's fine. Sort it by creating a This is not what I wanted to do. texture manager, make it an input here. So texture manager, I do texture manager. So I go, takes an input. This is fine. This is fine. This is not fine. Okay. Now render device create. When in fact, there is a nice little surprise when we get here because we don't have that inside app state since we don't have texture manager anymore. Remove that. App state doesn't have texture manager anymore. Here's that. Remove that. Go back to apps C++. Remove that. And this entire part of texture manager just gets cut. And pasted into the device creation. So after limiting frames, we get texture manager. So we included that. Memory is called mem in this particular function. Render device is not in it yet. That can be an issue. So what are we going to do? The render device is not in it. Instead, what we will do is we will not initialize texture manager inside render device constructor. Okay, let this be set to null. All right. That is just fine. We will go back there. We'll remove the texture manager from the constructor as well. Okay. So far, so good. And we just need to build the construction function. Where do I want to install? Okay. Yeah, we just need to be here in the construction functions. Take the texture manager. Instead of returning this, take render device, pointer render device, equals new allocation render device. Okay. We then allocate this. It does take a render device as a pointer. There's none of that. This is the destroy. If not render device, so it won't fail. Constructors are non-fallable in our case. If not allocation, return null, right? There's not allocation, return null. Otherwise, we create that. It will definitely be created. This might fail. If it fails, we do a application texture manager failed to init, create 10,000. This is fine. And now we need to say render device texture manager equals texture manager. Then we return render device. Okay. So in destroy, again, the first thing we do at the start after the is init is for texture manager. If it exists, we destroy. Oops. Okay. We don't check it. It has to be. So assert render device texture manager. Just assert it anyway, even though we have this line right there. We do. Isn't it? And texture manager. Right? Okay. So texture manager destroy. We will take it so that it doesn't remain anymore. This is fine. We should probably take from the frames as well. Take from the structural image views. Should work out. Build solution. Okay. That seems to be okay. So now we have render device, we have texture through render device. So when we go back to app state, I think we will stay we were in entity manager. Yeah. For the material, when we're trying to create this texture or sampler and everything, we will remove these three. So once it's loaded, we don't create this anymore. No calculating mid levels, no creating that. Okay. We're creating some resource ranges and views. All of that is unnecessary. Instead, we directly just say render device dot texture manager, create texture. We give it BVK extent. So blue edge was width, height, and 1 as the depth. This create texture will give us the render texture, but auto text where equals optional of RID of this thing. That is all right. If not, so we're going to actually write texture top. If not texture opt, we will not. Okay. If not texture opt, then we need that buffer to be deleted. We need to log that error. Both of them same things. We need to delete the STB data. So STBI free. And that will be texture data. Right? And we return null pointer. Okay. So that is an optional. We've gotten this that it's not true. Like if it's not true. So here the optional is true. So texture ID, texture equals texture opt dot value. That's guaranteed to us. Sub resource range. Oh no. We are using the same sub resource range here. And since we removed it, we don't have like the same sub resource range available here either. Sub resource range. There we go. It moves the mid levels, which we completely do not have access to anymore. Texture manager, calculate mid levels, static, move it to public interface actually. That allows us to use this publicly. That way, this mid levels can be calculated using texture manager, calculate required mid levels, width, height, and 1. This requires a texture, which is nothing but the texture ID, so texture manager, so then the device, texture manager, fetch image for the texture, value is why not, right? Depth level is -1. So we take this, new in 32T map levels equals that. This is just map levels. Everything else will use the right ones. Texture gets replaced by this. So I'm just making that call again and again. I should probably cache it. So undo all of that. This is fine. This is fine. And after net levels, I will cache this. So pk image texture image equals that. think I'll move it up to where we got the texture from. So yeah, that won't work, but that will. All right, so we have texture image. Now, texture image. So it will copy it. I can search that and replace it with this. So 1, 2, 3, 4. It needs an image created for extent, which doesn't exist anymore. So width, height, 1. Texture is no longer an image, so texture image needs to be taken in as an input. Texture image again, texture image again, texture view. So we don't have this yet. So we say image view equal texture view equals render device, texture manager, fetch image view, texture dot value. That gives us all of that. Texture allocation doesn't exist anymore, nor does the material have any need for it. So instead, material will only take a texture now. And we will go to entity manager tab H. And here, for a given material, we will switch this to requiring only texture ID. Texture. Okay. Now, one of the issues, let's say, texture manager is automatically created here. It should not be. No, sorry, it's automatically included here. It should not be. So then, to do remove this dependency. Okay. Now, what's the issue? Texture ID needs material or texture. It does not support any features like that. That is fair. But we can check if it's null or not. So RID operator do return index equals 0. And we make the const. So we can do that. Area solution to reference a deleted function. The material default constructor is deleted because RID is default constructor is deleted. Or at least it's not public. So fine, we make the default one public. Texture view is not a material. Yep, we're trying to destroy image views. We're trying to destroy image. None of this is necessary anymore. Because we can just take the regular device, let's say texture manager, retexture, entity, material, texture, and it was for itself. Succeeded. Let's try running it. Runs perfectly fine. Any leaks? Yes, plenty of leaks. Okay, let's see what it beacons. Invalid image view 0x CD. Okay. Why does this happen? The answer is actually rather simple. It's because the memory is not set to 0. What I will do is I'll do the simplest of possible things, which is when I get a new memory here, when I get the return val, I assign it to 0. So num set rect val 0 size. Hold then that predict is still a problematic thing, right? Which is not non-random, it must be a valid index ID. So what happened might indicate a bug. What happened might indicate a bug. Okay. In texture manager, then destroy textures, retake everything. Did, did, did. So this should be fine. So let's look at the destroy function here. This file, the abort has been called long before. So it's a VMA assert from destroy image here, from free texture here. So was it a valid read? It's 0. Okay. Oh. Oh no. Oh, no. So currently 0 is considered like 0 is considered a valid read, right? Because there exists like null is still a valid RID. So that is causing troubles for us because this goes in. It tries to free that texture with RID 0. So what I will do here is inside valid ID. No, inside the constructor actually. Where's the constructor? That's show manager. But there. So when I'm increasing the index, I'll also add it with generation mask. No, with one or it with one shifted by generation offset. So this is start default generation is 1. Okay. So by doing this, we've effectively said generation 0 for everything is invalid. Again, not really what I want to do. Ideally. So we do fix this by creating 0, 0 has a valid texture. Okay. So we come to Bindless node. Now it should be an issue, I think. Oh, it is an issue. Alright, what happened? So let's try it again. So it's fine. We get here. So the free list is a valid list. The prev is null, but the next exists, and it contains plenty of objects. Is it working? Second one, immediate second one failed. Why would it fail? The answer is, well, fairly simple. But iterating to the free list. And this sets like one node to 0, which is bad for us. Okay. So what we instead want to do is to pop the nodes from here. So for, let's say, free list node pointer node equals free list left. So we'll do it like this. While tree list and free list are empty, while it's not empty, we take a node which is nothing but an free list dot pop front. Doesn't matter what order we go in. So once it's been popped, this is a little required thing, right? Yeah, better, but the samplers have not been destroyed. Okay, each of these entities is creating its own sampler. There is a destroy sampler right here. So why is it leaking a sampler? Answer, I am creating samplers and I'm creating textures. I probably copied the code. Yeah, so right there. Don't know that. So now saving the samplers. Build, run, and perfectly managed. So textures have been managed now. That should be it. With the end of today's stream. Well, second stream today. But we haven't gotten yet to to Bindless. So we'll do that the next time. Thanks for joining. See you next time. Enjoy.